Okay, good morning to all. Am I audible?
Yes, sir.
So today we'll very quickly brush up our peripheral interfacing and the same devices what we have used for 8085 we'll be using here, but the difference would be that we do not need that 8255 or so. And we have observed already that the 8255 similar to that is already inbuilt as a port, available port in the 8051. Also the 8251, the serial communication, that is also available inside the chip, and so we can directly use them. So we'll start with that how to write our program. So it will be again the repetitions of what we have observed with 8085. And in this case, we'll be using the 8051 instruction set. And so the overall structure of this RTOS I have shown with the 8051 instruction. That's why I have written RTOS in 8051, but it is universal structure. So you can do it with any processor, even the new processors like ARM or so. And so the initializations part. So before we write that initialization module, we write this address vectoring. And this is because we have repeatedly justified that in the initial locations of the memory, we have the vector addresses of different interrupts. And what we want to work with multi task system, okay? Or we want to develop that. And so we have a set of tasks which we want to implement with these. And since this processor is sequential in nature, so we have sequential processor. Now, why is this so? Because of single ALU. Okay, so we have single ALU, so that ALU should be used for all the operations, whether it is arithmetic or so, and therefore we have to go for time multiplexing, time and ALU multiplexing. Okay, and so this time multiplexing we can do using the timer interrupts. We have already seen that how to generate the time slots for different operations. Like, so we'll be again recapitulating that in these slides. So we have address vectoring part, and then we have macros like say tcn, reg. So we want to, so this range or this equal, so that varies with the assembler. Okay, so if you are using the as Proteus assembler, so this reg we have already seen is replaced by this EQ, and equal is also replaced by EQ. So this is in Proteus. While this part, what I have written, it was from my own assembler. So there we have used this reg and equal. So that's why I have given this information to this assembler, and caution, the syntax is assembler specific. Now we have initial module where this part of the code will run once at the time of power on. Okay. And then we have an infinite loop. And so here we can place the foreground or non-time critical task like keyboard displays, right, like that. So we can place all those in a sequential manner. And so any timing changes or imprecision in the timing of calling these functions will not affect the overall performances. Okay. And then we have interrupt module in these locations we mentioned this way. And then we can write those like we are generating this square wave with the CPL instructions at the P1.0. But this time is highly precise because at every the basic time interval what we can set here for the timer 0 or timer 1. So the this part of the operation will execute very precisely at that time. And so we have divided into foreground or background or time critical tasks. And then we are placing either in polling mode or in interrupt driven mode. So we call this polling mode. Okay. And so in initialization module, so resource for time interval generations, we need to decide the design issues are which mode we want. So accordingly, we have to equate or configure that T mod. So these values we have already seen how to use that one. And then computation of content to be used for initialization of timer that we have done already. Then these time interval generations, we have used this, although you can see that this is not a unique solution. Okay, so any code which is dependent on algorithm you used is may not be unique. So that means that if we can find two solutions provided by the students are same, so there is a chance they are copying each other. Okay. So you may have think, so if you are thinking alone, then your code, there is a chance that your code is unique, means different from others. Okay. Otherwise, so that's why I insist you to think by yourself, put effort before the exam, long enough before the exam. Okay. Or if you not get time enough, so you have to face the time with hard working, right? So don't waste your time in other works which are not necessary at this moment. Okay, and work with the simulator. So I think that problem I have given the solution, you could solve it properly. Anshuman,
Yes.
that new simulator, okay, problem we had faced last time.
No, it's
So
working.
yes, it's working, right?
Yes, sir.
Okay. So now you have already seen this code. So we have moved this end and CJNE compared and otherwise decrease, and then we again stored that one and return from these. And so this is our, if I put any operations here, this will be our, as we have seen, like 200 microsecond. Then depending upon this tcan, we have seen that we have generated, say this was 200 microsecond. and then Tken was this 5. Okay. And so this is 1 millisecond time interval. And we can generate this way multiple such interval, right? So that's why. So this is very useful for developing our RTOS, the background one. Then we have this configuring port. So this is actually required in the initializations module, init module. Okay. Vector addressing, we have already discussed this part. Then run module, so we can put these polling based operations within this. And we have this infinite module, infinite looping. Okay, so this is must, so that our system works continuously. And so if we do not use that timer interrupt, the main program will run continuously, okay, in time. If this interrupt is given, so main program will intermittently go to the ISR, then come back main, then go to the ISR, and like that it will do. Is it clear to you? This is very important because it will give us the advantage of easy debugging, easy understanding, and so any code can be readable properly, and you can introduce new features, new functions very easily, either in the polling section or in the interrupt section, right? And so this will help us to develop and debug our code very easily. Now this interfacing this key, this part we have already discussed, that what are the different keypads. So like these, we have this common, and then we can connect these, press this one. So a push buttons, right? Then we have this matrix push button. So all these concepts which was used for 8085. So the same thing can be used here. Just we have to write our code in 8051. Okay. So we have also seen that why we need debouncing. So that we have already discussed in our earlier videos. So if you have forgotten it, you can go through and brush up your the earlier lectures. Okay, understanding. So we need to make our software solutions robust, right? And so we have this time delay. Experimentally, we observe this 20 millisecond. Okay. So I'm very quickly moving. So if you have any question, you can stop me and ask so that we can discuss a little bit and then move further. Okay. Again, now you can see that this key scanning can be placed in the infinite loop or in the main program, or we can put it in the interrupt driven. So whenever there is a key pressing, that time only the CPU will take care of that. Okay. So for that, we can do like this key 1 to F, and then we have this pull up register. So these are pull up registers. And then we can put it into INTX. So that means we have this INT0 or INT1, which is external one. Okay. Interrupt. So where are these? Which port? In P1, we have this one, right? So what is this? This is AND gate. Now, if there is no key pressing, so what is this voltage level? All are 1. So that means it will remain 1 for no key press, right? And then it will go down whenever any one key is pressed. Right? And so this can be connected to the INT0 of this. So when there is a key press, this will generate an interrupt. And so we'll move to possibly this INT0 is at 003 hex. And there we'll going for SJMP KBD read. And then at that address, so we'll write this KBD read. Now this label will be taken care or addressed by the assembler itself. We do not need to do that. Now, whenever it is coming, the program counter is pointing to this location. It means that there is a key pressing. Okay. So what is needed? So in this case, it would be better that if you debounce the circuit in the hardware itself. Okay. And then this can be connected to say port 2 of that. And so whenever it is coming, so you need to read that port, right? So you need to read the move A comma, say port 2. Okay. Now I am writing port 2. That does not mean that you should write this port 2 directly. You have to follow that macros. That means this P2 is equal to that address is available, right? So maybe say 98 hex. So you check from our earlier classes that what is the exact address. And then you can use this port 2. Okay. Sometimes the assembler is also giving us, so we do not need this that time. So assembler can also directly give us this facility, so we can use that port 2. So you have to be very active or aware in that, not that just I am writing, so blindly you will write, or your friends are writing, so you are also blindly writing. Anyway, so we read this. Now we want to see that. So we have say this is 16. So in that case, we need to read 2 ports, right? Or we can arrange in certain way that it can be read in 8 ports. Okay, so it's then a P2 and P3. And so you can move B from P3. And then you can go for finding what key is pressed, which one is pressed. So this INTX will not give us that which key has been pressed, but we can do it in with this logic. So logic operation for identifying keys. Okay. So once you find that keys, then you can do the corresponding actions, like say key 0 is pressed, which is symbolized as say 1, and you want to display it to the display unit, so that you can do. Or 1 is displayed, or 1 is used for summing up 2 numbers. So first number is 1, second number is another key is pressed. And so you can make a calculator out of that also, right? So our purpose here is to show that how we can utilize this keyboard in an interrupt driven way. And we can do this. Sometimes we have the hardware directly where you can,
Sir,
yeah. Tell.
Sir, instead of using two port to get the 16 pins, can we not use a encoder
Yeah.
16 to for
Yes, yes,
encoder?
you can use that's what I was going to tell you. Okay, you can use that one. I said that now that if this can be done these two ports, or we can use that encoder and we can find it using only one port, single port, right? Now here, all of you can notice that for a same problem, we have multiple solution, right? And so we need to find which one is the elegant solution. That means it will reduce the cost, but it will not hamper the performance of the system at all. It will improve the resource utilization. It can improve the timing, or it will not drastically reduce the execution time, or improve, reduce the speed of operation. Okay. So very often those issues are coming, and you have to be very thorough in that understanding that which solutions would be better solution. Okay. Now, during the exam, you may not come up with some elegant solution. So you have to accept that this is my limit at this moment. All right. And don't say that why I am not getting this or that. So to have that solutions, your solutions to be elegant, you need a lot of practices. So if you have really put effort, you will definitely can come out with those type of solutions during examination also. And if you really do that, it will help you to sustain in the industry also. Because the industry is very competitive in nature, you are getting paid. And so if your solution is not sellable, you cannot sustain in the industry. So just don't get sympathy, means make a sympathy on yourself that I cannot do, or I have this problem or that problem. But be professional in that and be expert in this. Okay. So we can have different ways to implement these interrupt driven modes. Like we can also use this type of configurations, these 8x8 keyboards, right? And then so this goes with the keyboards where you can input from the user end. Now again, we need in our engineering domain or so to interact with the signals and systems. Like that day we had discussed about to measure the speed of a motor using the tachometer, and we want to have a digital solutions of that, right? Now, very often we may not get the signal coming out of the system as digital one. So we need this ADC, which we have already covered during that 8085. So the principle of this ADC 0809 is already known to you. And so I am not going to discuss very detail in that. Hmm? And then we have also used the DAC. So DAC 0808 only. So we are just replacing that 8085, and then we are working with the 8051. The advantage we are getting here, we do not need to use additional peripheral interface controller like 8255. Okay. And so that will definitely reduce our cost. Okay. Now, this is one code which I have written with my assembler. So that's why some of the instructions you may not get in the Proteus. So you just change those. You can change those. And I have, I'm showing you because you need to understand how we can develop our code professionally. Not just we are writing for any purpose or any way we are working. Okay. So you should have a prelude in the beginning that what this program is going to do. when it is written and who has written, and then you can add a version of that if you are thinking that this is not the final one. And then you have to give a hardware descriptions in these. Like I have written here, the ADC is connected to port 1. So port 1 is connected to ADC output, the digital output of ADC. Then port 3.0 is connected to ADC ALE, and a low pulse is required there. Now this a pulse is required, low high pulse. Okay, pulse is required. Then P3.1 ADC start conversion, again pulse required. Then P3.2 ADC EOC, and which is actually connected to external interrupt 0. So INT 0. Okay. Then CBA. A is the lowest LSB and C is the MSB of ADC configured hardware for channel 1. So it means that we need to have this channel 1 means that the address is 000. Okay. Or if you can identify it as a channel 0, channel 1 up to channel 7, or channel 1 up to channel 2. So it depends upon you, right? So this can be written like that. And then the V reference is 5 volt, V reference minus is ground. Clock of the ADC is around 640 kilohertz. And then DAC is connected, input of DAC is connected to P2. And for demonstration purpose, we can use the example signal of amplitude 2.5 volt with a DC offset 2.5 volt. So which makes the values positive, and the frequency can be anything. We have used 50 hertz. We can use that one, right? And so then we start our coding, that SJMP main, then SJMP ADCRD. So we are reading that one, where at the external interrupt locations. Then to make our coding easily readable, we have used ALE in for the P3.0, SC for 3.1, EOC for 3.2, and then we have this tcon dot 0 bit, which actually sets this external interrupt either edge triggered or level triggered. So this is used to set for falling edge triggered interrupt. So at the INT 0. Okay. And then we go for initialization, where we are setting this P1 as the input and P2 as the output. Then we are setting this I with the IE content and setting this INT0 edge so that the interrupt occurs at the falling edge. Then the first conversions, we are starting with set B ALE and then set B AC. So you observe this, that we have set this ALE, and then, so this is our ALE. We are not resetting this ALE. Before that, we are setting this SC. This is to make or ensure that we'll at least get this amount of pulse. So after that SC set B, we are clearing the ALE. So we are clearing that ALE. And then after clearing that ALE, we'll get this. So this set B, say it requires 12 clock cycle. Okay, so it means that this will be at least 12 clock cycle. So what we did, instead of putting a knob in between, we are utilizing the set B SC as that time delay for this pulse. Is it clear?
Yes.
Okay. So, and this set of instructions we need for number of times continuously. But when we start our program, this should start with the first time for first sample collection. Okay. So we have already given that in the comments. So for example, say if I had not given this comment and I forgot that what is that time requirement for this set B SC. Okay, so it would be difficult for us, say for 5 or 6 years later, I completely can forget this, but the comments will help us to recapitulate that one. Okay, and then we go with this foreground sjump foreground. So we are not doing anything in the polling mode. And so what we have to do here, that we push and pops, this is just to ensure that if anything is inserted here, that particular operation is using the accumulator, so then it will not hamper that process. Okay. So very often, because of these, our functions get stuck or malfunction, and then we are unable to do some debugging operations. So these are very tricky situations happens, that because of the stacking or improper stacking or not stacking, so the values can change in with inter operations or inter subroutines, and then you are not able to debug that properly. So you should be very careful with that. So that's why it is a good practice that if you write any subroutine and whatever registers you are using, which are very common, any other fellow can use that one. So in that case, you push it and properly pop it. So once that interrupt occurs, so when that interrupt will occur, now what is the conditions of EOC? So whenever the conversion is carrying on, so this is conversion time. Okay, conversion period. And so you can see that whenever the conversion is over, there is a positive edge, right? Okay.
Yes.
So what I have not written here actually. So what is needed, we need to pass it through an inverter so that we can get a falling edge there. Okay. So this would be connected to microcontroller, and this is from ADC side. Is that clear?
Yes, sir.
Okay. And so we can read that one. So read ADC. And then this is a pass-through example. So what does this mean? It means that we are not doing any processing on this. We are just simply passing it to the DAC. Okay. So that after the DAC, we can get the same signal which is given to the ADC input. So that will ensure that our code is working. But when this will come for this first time we have given, so that sample will be collected. But for next sample collection, we should re-invoke that same set of instruction before we go back from this routine. Is that clear? So if we see from the signal sampling point of view, say our circuit has started its operation here. So that means that ALE and this SC has started. Or instead of that, let it be like this. Sorry. So it has started somewhere here. and then it will take some time, so that conversion time, so it will get that sample, then it will take some time, right? And then after some time, so after some time, say this one, so this is where this EOC is at this rising edge, or the inverse is falling edge. So the microcontroller or the ADC output can be read. Now, again, the start should be there. So after reading this one, at this point, again, this start and ALE signal should be there, so that it will get this one. And after that conversion time, it will get that EOC. Okay. And it will continue this way. Is it clear? So I have exaggerated this time, but this is very small amount of time. Is it clear to you?
Yes, sir. But sir, in this circuit, we are not considering any time like delay or for DAC or anything like when it is ready to take the data.
No, we are not using time delay, but we are using the interrupt driven concept, so that whenever this conversion is over, this EOC will indicate that the conversion is over, and the CPU will read that one. I have shown this time lag exaggerated, so that we can have a clear idea that what happens.
I am saying that we are pushing the data to DAC without even like checking if it is ready to take data or not.
No, in case of DAC, it is not required. Okay, because DAC, you see, this process is actually very fast, so you do not need to do that. You see, this P1 is read, then you have transmitted, and the DAC is complete hardware. It will work immediately, very short span of time. And then you are again starting that. So then again, this will take, say, 100 millisecond or so. And so before 100 millisecond, you already get this DAC output, because this is not a software one. So delay is very small. Okay. So tomorrow, actually, we can see the demonstration of this code. Then we have this interfacing displays. So we can do that 7-segment display or the LCD display. So maybe for this time, we'll not go for this LCD display. And 7-segment display, we have already learned it. Okay. When we study 8085 and peripheral interfacing. Okay. And so I can keep this for you to learn by yourself. By the strategy of learning already discussed in this course. Okay. So for the time being, this won't be in the examination, but for your future and your interest, you need to learn it, and it would be better if you learn it. So these are already we have covered that the structure of these 7-segment displays and how we can connect these pins to the microcontroller port directly. Depending upon that, this code will be generated for numerical values, the display values. And we can have, say, one examples of that, like with a single unit that we can connect. This way, we have common anode, the controlling contrast, and we are connecting it to port 2. Sometimes we need to connect pull-ups, okay, so that we do not have the interfacing or interference problem, okay, and the logical deviation problem. So the voltage level should not get down. So if this device draws more current or sinking capacity, then it provides the microcontroller device it. So the pull-up will be essential for that, right? And then we can also connect the multiple display unit, right? Using this configuration with these, say, this is connected to all these display 1, display 2, display 3, and we have a control on these common cathode and these common anode portions, right? We have already seen this also. And then, as usual, the display in hex, we need to convert that hex number into BCD. Here also we have found that DAA is there, but be careful this time that only single DAA will not convert a hex number into BCD. It will only do individual number, add with, say, 6, depending upon the conditions of the digits, right? Then you can use the index addressing, that means base address plus index, the nibbles of BCD number, to look up table for fetching the code for these 7-segment LEDs. Then send the code to port where these units are connected. Okay. So today we are not going into this. There are similar way, similar strategy you can utilize to work with LCDs. Right. Now, we can go with the device communication, which we have also come across when we studied the 8085, and we already know that what these UART standards and SPI standards are there, and what does this transmitter and receptor is doing, and what is should be known to us, the baud rate should be known to us, the frame structure should be known to us. Known to us means both the transmitter and the receiver units. And so what we need to know what is inside this 8051. So UART baud rate generation logic, where we can use the timer 0 or 1 or timer 2. We have already seen this circuit, right? How to generate those clocks. Then we have SBUF transmitter, and then we have SBUF receiver unit. Okay. And we have this TX control and RX control using this SCON register. Okay. So we need to study this SCON, what are each bits are defining. Then this logic can come from this timer 1, timer 2, or timer 0. And then we have a TX1 and TX2. So this is analogous to (8251). So there we did not have to make the frame, right? We have only placed the data, and this TX control unit will do the remaining job of making that frame using this adding this start bit and then adding the stop bit, or the adding this CRC bits which for error checking, right? And we also have different frame rate error detections units, or so we can use the status of that from there, right? And here, like just like 8251, we had to set the address and all, so we do not need to set that. So this is one advantage which reduces our effort. Okay. So in the SCON, we have this SM0 serial port mode bit 0 and SM1 mode bit 1, and then SM2 multiprocessor communication enabled. So this bit can be kept to 0 if not working with multiple microcontrollers. And then we need to see what these are doing. If we want to enable the receive, this bit must be 1. Now this TB8 and RB8, so transmit bit 8 and the ninth bit in this case of mode 2 and mode 3. So these are the configurations we can do. So one thing we need to understand is TI and RI. So this transmit flag set when the byte is transmitted completely. Now here we need to also observe that this is our TI and this is our RI, but also this is going through the ORing. So this is TI or RI, and this is generating the INT, okay, interrupt. And the vector address corresponding to that is 0023 hex vector address. Okay, this is internal. We do not have access externally. So whenever there is a received data or the microcontroller is sending a data to this, so this interrupt can be generated. So whenever there is a reception, say for example, it will interrupt the microcontroller and microcontroller will read this data, right? Now in this case, whenever one data is transmitted, then it will generate this interrupt, and then microcontroller can send or write the data into the SBUF for the next transmission. So from this structure, we are able to relate with our programming structure that either we can place this in the polling mode, and there we need to check the TI and the RI, or we can go for interrupt driven mode. That means our code should be written into this. So code should be written at this 0023 location. Okay. Is it clear to you?
Yes, sir.
So we can check this, or we can use the interrupt driven mode. Now what is this SM0 and SM1 tells? That it will actually fix the baud rate. Okay. Now if SM0 and SM1 is 0, it is mode 0, and there is another bit in PCON register S mod 1. So depending upon that S mod 1, the baud rate can be varied, but here it is don't care. So it is only FOSC by 12 in the mode 0. In mode 1, we have the options for S mod 1 as 0 and 1. And so this B0, which is set by timer 1 and 2, and if it is 0, And then if it is 1, then it will be just twice of that speed. Okay. Similarly, for mode 2, it is fixed one of FOSC by 64 or 32. And in mode 3, we can set it by this timer 1 or 2. Okay. So if we we want to set different baud rates, we can do it using mode 1 and mode 3. Okay. So it is just recapitulation of that how this timer 2 can be utilized to generate these baud rates. Okay. And in case of timer 1, again we can have for is mode equal to 0. So this baud rate can be set by this. So this is BQ and this is our content. So what should be the content or initialization content? Okay. So initialization content. So 256 minus this one. So it will give you the required baud rate of this value. Whatever you decide, say if you decide it to be 9600, you can decide this as 11.059 megahertz. Okay. And if you calculate this, whatever value will be coming, that should be sent to this TH1. And for the case of S mod 1, it should be just it is half of this. So that means this is the speed will be going by double or that, right? And then what you need to do, you need to clear this flag and then you move SB, SBUF and the character. So this is our character we want to send. Okay. So this will actually provide you the ASCII values of that. Okay. And then in the looping, we are checking that one, right? So check the transmission is over. And in the receiving one, so this is essentially we are placing in the polling mode. Okay. So we are only checking that RI. And then once this is over, so JNB jump if not bit, that means the bit is 0 whenever there is a transmissions from the other end and this SBUF is getting that data. So once this is over, it will be, so RI will be 1 once fully received. Okay. And so it will come out of this loop and then we can read this SBUF to A, receive data. And then if we want to communicate with PC, we have seen that we can go with these RS-232 protocol. So we need a logic converter in between and we can use this 232N for the PC side and the CMOS or TTL-N for the microcontroller side. Okay. So this program actually shows you, though I have used this LCD, but you can replace this LCD by 7-segment LED. Okay. For the time being. And then we can work with that, right? You see that we have used this 0023 serial communication, the subroutine. And then in the main routine, what we are doing, we are enabling. So notice this IE content, enable the serial interrupt, timer 1. Okay. So timer 1, we can go for optional one. Apart from that, this T mode, then SCON, then for baud rate for 9600, we need to set it TH1 as FD and TL1 FD, right? Then we start the timer and we have to set it in the, timer 1 in mode 2 auto reload mode, right? And so then, so this is for, so you can replace it for this LED init. Then we do some storing count register, okay? And then we have this main loop, but we are putting our code in the serial. So this part is for initializations of LCD, so that should be replaced by your LEDs. And so in the serial COM, we came to here and then we have to check whether it is due to the RI or due to the TI. Okay. So we are trying to receive that one. And then if it is JBC, so jump bit on bit and clear it. So we can use this one directly. So till that RI is 0. So whenever RI is 1, so definitely it will be 1 whenever there is a reception. And so it will go to receive bit, then it will read that content. Then you can go to the, so this part is for debugging. So this is, I have used for debugging. I want to know that whether the ASCII code is coming correctly or not. So that's why. So this is not needed. You can put it semicolon there. And then you can, so this code is actually related to that LCD code. So what you can do, whatever data you are getting, you can send it to the LED segments for the display. And what is your system? Your system is your PC, which we can do it in the simulator, Proteus simulator. And then you have your microcontroller based system. And then you have this RS232 port pin where you are connecting this MAX 232 converter, and then it is connected to your TX and RX line. Okay. So in the terminal, so application, you are inserting, so input character, and this microcontroller is connected to the LED units, right? So say I have used this one should be displayed in 1 unit, say. So we can do this way, right? So this will send, transmit, this will receive. So this is receiver end. And this is transmitter end. And you can come up with the full duplex mode of communication, right? Sorry, this should be this way, and this is reception way. And similarly transmission, so this should be connected to the reception, and this will be transmission. Okay, EX, RX. Is it clear to you? So here what I have done, I have give you the hints, you can say, that how you can connect your system, and then how you can use the interrupt driven serial communication, and you can display a character in your 7-segment LED, because we have learned the 7-segment LED part. Okay, so remaining part is related to LCD, so we do not need that one. Okay. And so we have these examples of this one. We can also measure certain temperatures, say using the thermistor or thermocouples sensors. And each sensor will have a transfer characteristics. So depending upon the temperature, say 60 degree, so I can measure a resistance, the value of that as 6K. And so this can be converted into the current or voltage. So that voltage can be passed to this ADC and then to microcontroller. And then if you want to display this temperature, to display unit. Okay. Is that clear how we can go with the different operations? So every sensor will have a transfer characteristics. And then if it is linear, so that will be easier for us, that we can have a integer multiple of that value, which will give us the signal in terms of current or voltage. And then that voltage signal can be fed to this ADC, get the digital value, find this RK. And from these expressions, we can find these expressions of the temperature. And that temperature we can display in this display unit. Is that clear? So I suggest you, all of you, to go through this video particularly because this is very quickly we have covered, but this is not difficult because we have already read this part, right?